This is Physics 2211, Lab 2, and the purpose of this lab is to observe the trajectory of an object that is moving in a projectile motion. We will use models from Tracker and GlowScript to observe the predicted versus the observed data, and starting off with the fundamental physics principles, we have the position update formula, which states that final position is equal to initial position plus the average velocity times delta t. And then we have the velocity update formula, which states that final velocity is equal to initial velocity plus the net force divided by mass times delta t. And we were also told to use the drag force, which is equal to negative b, where b is the proportionality constant, times v squared, which is the magnitude of the velocity squared, times v hat. And we also have the constant of gravity on Earth, which is 9.8 meters per second squared. A brief preview of the results is that the observed data is a little different from the predicted data, but they show roughly the same idea. The system is a paper ball of mass 0.0181 kilograms. The surroundings include a ruler, bottle curtains, etc. And the initial position is 0.359 meters in the y direction. We started off at x equals 0, and the initial velocity is 0.6273 meters per second in the x direction and negative 0.1125 meters per second in the y direction. And here's a picture of our experiment. As stated earlier, we threw a ball from a height of 0.359 meters in the y direction and observed it going down using Tracker and GlowScript. Here are pictures of my code. On the left, you can see our initial conditions again, along with the drag force being set to 0 on the bottom to only show gravity, along with the top where it's just showing an estimated drag force. And on the right is our computation in the code using the position update, the velocity and position update formulas, along with how we found the force of gravity and drag. And here are our position versus time graphs, position in the y direction for, on the top left, Tracker, top right, the GlowScript without the drag, and on the bottom, GlowScript with the drag. And here are our trajectory graphs, all on the same chart, with x on the vertical and y on the horizontal. And as you can see, they show roughly the same idea, but GlowScript seems to show that the ball will reach the ground much faster than it actually does. And this could be due to a number of reasons, such as human error, because it was a little hard to see the ball in each frame, errors in the software, because we may have set the proportions a little off, or outside forces may have acted on our system, such as an air conditioner, etc., or we may have chosen a weird proportionality constant for drag. Now, do any of our models show a terminal or predict a terminal velocity? The model without drag from GlowScript seems to show terminal velocity, but we could revise the experiment for it to be done at a higher height to try and better get to a terminal velocity. Now, what if we had instead thrown the ball straight up instead of at an angle? Then it would have taken longer for the system to reach the ground, because if we rearrange the kinematic equations, which we can get from Newton's second law, then we can see that in the way that we threw it, the first, where we have vi times sine theta divided by g which is the time it takes for the system to get to max height at an angle, then we can see that would be less time than if we had just thrown it straight up, where we have v just divided by g, which means that the ball would reach the max height much later and thus get to the ground later if we had just